So I'll just wrap up my slides here quickly. And I promised to explain how we simulate these readout circuits. I won't be able to do so in great depth, but I'll give you the high level. So I introduced these Purcell filters and showed we want to simulate lots of them coupled to one feed line. And the flow chart is here. So normally we would go ahead and we would lay this thing out, and it's really complicated. And simulating this thing here with the two modes and the two line widths takes an hour per iteration roughly, using something like HFSS. This here takes not even 3 seconds. 3 seconds is an exaggeration. It's like less than a second to simulate this. And using the techniques we talked about, like capacitance to ground, it's accurate. Importantly, we need to know how that modeling works so that we can also translate it to a layout at the end. And so the pitch is that we optimize. The pitch is the following. If we want to hit certain frequencies and line widths, we won't play around with our layout until we hit those, but we'll play around with the circuit until we hit those. And then we just translate it. And so this iteration loop is much faster. And so I'll just show you the results from that. Or roughly speaking, I'll show you this thing here, where we are targeting Purcell frequency, resonator frequency, and the two line widths. Like so the line width of the Purcell filter and the coupling strength between the two resonators. So these are 4 parameters for 5 resonators. And then there's also the feed line length that we want to tune. So that's 5 parameters for 5, in our case, resonators. So it's a lot of elements. And we're playing around with the capacitances and the lengths. That's what we're playing around with. And so we write this optimization loop that has the following results. It looks like this. So we start off, we first optimize all the resonators individually. So we reproduce a guess for how to choose our circuit values, and that produces something that looks not great. But we fit to it, we extract what it delivered, and then we just update our circuit parameters again accordingly. So it's like a gradient search, if you will. And then after just 5 iterations, you reach basically your targets. And you can see the relative error goes down really fast, exponentially kind of in just a few iterations. And this takes less than a second per iteration. And then once we've optimized the resonators individually, we stick them all together, and then we optimize further. And this takes maybe another 10 seconds per iteration, or 10 seconds in total. Sorry, this is in total, it's not per iteration. So the other one was like a second for 5 iterations. So this is 10 seconds in total. And you can really see here, you go from a relative error all the way down to 10 to the minus 7 to 11. So you really hit your targets in just a few seconds. And this is all numerical. So that's really nice. And now we want to see some data. So here's some really cool data where the red curve is what I simulated, and then the blue is literally what I measured. And so they agree really nicely here. And if we look at a slightly bigger device, or not a bigger device, but a few more samples, we see this over here. So this is, I have four devices. It's basically 4 copies of the same thing, but they target different frequencies and line widths. So here, kappa P is targeted at this dashed line, here at this dashed line, J is targeted at this dashed line, and so on. And here the frequencies are targeted at the gray dashed lines. So you can see these are for different targets. And here the resonators are also detuned by, yeah. So it's just different targets. And the punchline is there's good agreement. That's really encouraging. And we do notice that kappa P has a bit of more noise or variations. But this is expected. What you see in the different colors is different cooldowns. So I take the same device and I change things in my setup. Like I put an amplifier in line. I change the cable that I'm using, and this stuff changes. So what I'm saying is it's not entirely my fault that these are off, because this parameter is very sensitive to things that are outside of my control. The other ones are more in that they're a little less sensitive for sure. So what I'm saying is kappa P is very sensitive, and within the variations that we expect, we're well on target. And that's all we hoped for. So really the punchline is we get overall good targeting. We've also tested parameter sensitivity. We expect a certain spread, pretty large spread for kappa P. There's not much we can do about that in this architecture. There's other architectures we can choose to improve the sensitivity of kappa P. So this is just a shortcoming of this architecture. But all in all, and I'll end on this note, and then go on with the workshop, this ABCD-based simulation actually accurately captures distributed effects for standardized geometries, like these capacitive couplers that you've simulated offline, and it's computationally efficient and it allows for really fast simulation loops. Some comments, it's non-trivial to incorporate like radiative crosstalk, like I talked about how those assumptions are made implicitly, and also does not yet include nonlinearity. So maybe if you want to add qubits into this whole thing, things will shift a little more. We can extend this, and I would like to extend it one day by including things like EPR, which Zlatko also talked about at this conference. One could include EPR, which is also an efficient method to add the effects of qubits. Yeah.
Can you still do the ABCD simulation method if you operate at room temperature?
So at room temperature, your chip is not superconducting, so it won't look the exact same. So what that means is like a very lossy transition line now. You can incorporate loss. I've not tried measuring, or yeah, you don't really see the resonators. So do you want to comment on that?
I mean, microwave engineering.
Oh, for sure. Microwave engineering works at room temperature for sure. Just our stuff is more designed for cryogenic temperatures. But yeah, this is derived from stuff that works at room temperature. Yeah. All right. So is everyone a huge fan of ABCD now? I am. So now we'll head over to the workshop, which I'm really excited about, and I'll reshare my screen.
We will now move to the workshop online.
Yes, we will now move to the workshop. Yes, basically, I think what I should show you is, I'm just getting my workshop thingy. So what you should see is this is the folder. It's called, I mean, I don't know, maybe some of you use Jupyter Notebook in the browser. I'm using it in VS Code. Not really visible, but on Zoom it is quite nice. But if you open the folder, then you have this file here called workshop.ipynb. So you just want to open that. Yeah.
Possibly turn down the lights.
Yeah.
Okay. I think it's okay for that.
Nice.
Better?
It's better?
Go full dark.
Very dark.
Okay, that's a bit
That's a little dark.
Oh, that's full on.
Yeah, I remember.
No, we did.
If you did,
They open the gates actually.
Is it better? It's coding mode?
Yeah.
Nice. Coding mode. All right.
We
Cool.
actually see
So,
into the folder.
you just want to be in the folder to open it up. And then the instructions of what you need to do to get started are here. So you might want to create a new environment. I like to use Conda. Just set it to the most recent version of Python. And then you activate it, and then you just CD into this folder here using your command line tool. So, and then you just want to CD in there.
Can you increase the font size? Command plus or something? Of VS Code.
Yeah. Command plus.
Or maybe try view. Need to go to the settings,
Zoom
actually,
in.
Apple settings.
Yeah. So this is better.
We have to.
So you just want to, yeah, go wherever that thing is. Just CD into that directory and then hit install. Minus requirements.
ABCD.
And then let me know if that works for you guys. Okay. So that's basically it.
CD can use folder. Excel.
So let me say a few words about this workshop, and you can also not pay attention to them if you're just installing stuff. So the workshop, you'll write ABCD matrices. It's just filled with blanks, all right? And then you'll multiply. You'll simulate some simple networks. So you can just maybe we'll look at one of these tasks together. I think that's a good idea. Let's look at exercise 1A together. So I'll maybe wait like another minute for people to get started. Oh, and also in that zip file, there's also a PDF that just contains, sorry for the bright picture, bright slides, but it just contains the most relevant slides with like formulas that you might need. Okay. Yeah, it's just some slides that you might need. So if you want, you might want to open up that PDF on the side. I closed it. Sorry. Okay. So are we good to take a look at the first task? I'll just get started. So the first task, we literally just want to implement some of these ABCD matrices here. Okay. So here's an example. Here there's a function that says get ABCD series inductance. So here we need to implement the matrix for a series inductance that looks like this, right? 1 J omega L. So this matrix takes variables, the frequency array and the inductance. And here is its definition. So we're creating an array of ABCD matrices, one for each frequency point. And then for each frequency point, we write down 1 J omega L, 0, 1. That makes sense? So we have, this is the ABCD matrix right here. And we're just creating an array for each frequency value. So we're sort of already evaluating these ABCD matrices at each frequency point. Okay, so you just want to follow the same structure here and now fill in the blanks. So yeah, let me actually run this. So I have this QDW. So we can run it. And then I can check my implementation here by calling this test function, and it's correct. So yeah, if I change it, then it should be incorrect. So there's only one solution here. Right, and so your job is now to fill in the blanks for the series capacitance, the ABC transmission line, the transmission line, and a parallel inductance. And just follow the same structure as here, and you'll be well on your way. So I'll let you guys work on that for a little bit. Does this make sense to everyone? And Okay, I'll just get to you and feel free to start, working on yourselves. So you can just work through the code.
If you have
For everyone who is still struggling with installing and getting it to run, many of you are running into a problem with SVG write and some dependencies. So you can just go and comment out the first 2 rows here. And then the notebook should work until like halfway through, and the tests won't work. So there's still ways you will plot data. So you can, I guess you can call me, or you can just go through the notebook halfway through. So that's probably better than not doing that. So yeah, just comment out these 2 rows for now. If you're struggling with SVG write, and try to go as far as you can get. The intermediate solution, not a perfect one. I might just, so for those for which the notebook is working, great, just keep on pushing. And for those for which is not working, I'll just walk through it. And maybe I'll ask questions to make it a little interactive. So ideally, you can run these first 2 cells. Maybe I'll make it even a little bigger. So here's my screen. And the first task is to write these ABCD matrices. And so we have an array of frequencies for which we fill out the form that we discussed in the PDF, right? It's a series inductance is just 1 I omega L 1 0, right? So that's over here. And so here, let's just walk through the capacitance. The capacitance is just 1 minus I over omega C 0 1. And it's the same structure overall. And you can see that the series capacitance is given here as 1 0, and then you insert the series capacitance is given here as 1 over I omega C, and so you just insert 1 over I omega C 0 1. So that's what you see here. And then for the transmission line, we just go to the PDF and we fill out this thing here, these cosines, and importantly, apology for the confusion, this is not a double slash, but the length. This has caused a lot of problems for people, and the reason why the test evaluates is because I test against a length of 1. So yeah, that's not great. Anyway, or something like that. Okay, then finally, here we have the parallel inductance. So what I mean with parallel is the second row here. Probably a better word would be shunting or hanging. And here you just take the y here. It's 1 over I omega L, and you insert it in the bottom left corner. Okay, cool. So I'll just keep moving at my own pace here. Interrupt me if you have any questions. I can also keep checking. So Edward Thing, and yeah, why is there a minus sign? So that's a good question. It would be also correct for me to write 1 over and then 1j, right? So 1 over j or I, j and I is the same thing. It's the square root of minus 1. And 1 over I is minus I, right? So I can just use that transformation. That's why I'm giving this here. If you follow the PDF exactly, then you won't have a minus sign. So that runs correctly. So that's amazing. Okay, so the next job is, now we have our ABCD matrices. Now we need a function that takes our ABCD matrices and converts it into an S21 transmission. So here we go to this slide where the formula is given here. So it's literally just the matrix elements converted into this fraction. And so we'll go there. Here, let's study the inputs. So the inputs are the ABCD array. Again, remember we have an array of ABCD matrices, one for each frequency. So we've already evaluated them at all the frequencies. And we want to create an S21 trace, so S21 value at each frequency point. So we'll just go and extract the different matrix elements. So this, for those who are not aware of or not familiar with NP data shapes, this just says that I'm getting the top left entry across all the frequency, across all the array elements. So for each, this gives me an array of all the top left entries, which we call A, right? So this is now an array versus frequency. And now we get the other frequency, the other elements too. This is the top right, this is the bottom left, this is the bottom right. And here you can see that we've just computed the S21 function. Like here, importantly, you need to add the port impedance, which is provided as an input variable. Okay, so now let's run this and check that the implementation is correct. Cool. So now we'll do a very important step, which is implement matrix multiplication, right? And what I've advertised is the whole point about this formalism is we can get the full ABC matrix of a two-port network by multiplying together their matrices. And there's yeah, it's just a little more complicated than I showed you on the slide. Why? Because now we have arrays of ABCD matrices across frequencies, right? So if I want to multiply two ABCD matrices together, then I need to do that frequency-wise. So for each frequency value, I take the two corresponding ABCD matrices and I multiply them together. This function does that for you. You don't have to do anything about this function. All it does is it takes a list of the two ABCD matrix arrays that you want to multiply together, and it outputs the total ABCD matrix. So we can apply this for our first example here, where we have 30 femtofarads, 4 millimeters, a transmission line, and then a 1 nanohenry inductance. So here I'm providing all the circuit elements we need. And I think one thing I should improve about this is the phase velocity and characteristic impedance. They are defined at the very top in your first import statement. They're a little hard to find. I should have given them here. So some people have trying to deal with that. Apologies. But so here we have all these circuit elements we need to describe the circuit above. And there's also a frequency array that's created for us. So we don't need to do anything here. So now what we do is we create these ABCD matrices, right? So we create the ABCD matrix for the series capacitance first. We use the function that we wrote. Okay. Then we write the, then we get, so yeah, this function takes in the frequency array and the capacitance. Now the transmission line takes in the frequency array, its length, the characteristic impedance, and the phase velocity. So we get the ABCD matrix for that. Then we compute the parallel inductance, which takes in the frequency array and an inductance value, right? And this, so now we have our three ABCD matrices, and now we can just use the function multiply ABCD matrices. And like I said, the way this works is you just put them in a list, and it does this frequency-wise multiplication of the 2x2 matrices. So now you get the total ABCD matrix that describes this circuit over here. So let's check this, and it's correct. Look at that. So as a final step, before getting to really satisfying results, is now we want to convert this total ABCD matrix into an S21 parameter, right? And there's nothing we need to do. The code is already provided. Here's there's just a plotting function. We just run that. and then we just run this leftover cell that I didn't remove. Yeah, so we just run the cell, and luckily we've already implemented the function that translates our ABCD matrix into an S21 trace, and we've already checked that it's correct. So if we run it, we get a very interesting trace. So let's look at this for a while, and maybe I'll ask a question. What do you guys think we're seeing here? So you can see, in principle, there's like a trace that's going up, and then we have these hills. So does anyone have an idea what's going on here?
I think the capacitor just says that you can't get low frequencies, right?
Perfect.
So that's a slope.
Yes.
And then probably the transmission line has some resonance.
Yeah, so very good. Full score. So the capacitance is like a low pass filter. So remember, its impedance is 1 over omega, right? So a low frequency is a high impedance. Okay, a low frequency is a high impedance. So a capacitor doesn't really transmit low frequencies a lot. And so this leads to this trend going up. And then additionally, this capacitance at the input and the inductance at the output, they represent two boundary conditions. So signals will be reflected between these two. And if our frequency is at a, it has a wavelength that fits right between this length in 4 millimeters, that forms a standing wave resonance, right? So this is also a resonator. And it also has harmonics, right? Higher multiples of that frequency, of that wavelength, will also resonate. And these are the repeating patterns we see here. And so with just a few cells and a few import statements, we can easily simulate the complex distributed dynamics of something that might otherwise take a 4 millimeter cutout, which is a big cutout in an FEM solver, right? That might take a lot of time to solve. And I promise you that getting those simulation tools to run is much more complicated than my notebook. So maybe not, but I guess you'll find out in the course of this week. Okay, so that's a really cool first checkpoint. And I might pause here, see if anyone has any questions about what we did. So I'll just run down again that we've done a multiplication of the ABCD matrices for this circuit here. And then we've simulated its S1 trace, and it really lines up with our intuition. Cool. So now we're implementing this hanger transform. So the hanger transform just says, I have a circuit like the one we just created. And if I now want to, put it on its side and short it at one end, how do I do that, right? So I do that using this transformation here. So I just take its D and B entry and put it at the bottom left, and then I write this ABCD matrix. And so that represents when it's hanging, okay? And so here we need to fill out, the formula for that. And so again, we're going through this ABCD. So this formula takes in the ABCD array that we want to transform into its hanger geometry. And then we create a new ABCD matrix of the same length, right? One entry for each frequency. And then for each frequency, we get the D entry and the B entry. So that's the bottom right and the upper right entry. And then we just write this matrix, like on the slides. So we run that. We apply it to the circuit we created earlier by just passing the ABCD matrix that we successfully computed, and we check that the implementation is correct. And just to see that these things work, you have to, in most cases, these tests should work. Okay, and now we can use the same S21 transformation. Again, we have one total ABCD matrix. This is where we want to arrive at to plot the S21 transmission. So there's nothing you need to do in this cell, just run it. and boom, you get something very different, very interesting too. So does anyone, I mean, I guess I can just, yeah, comment on this thing. This, we recover very strong resonance, even stronger than before. But they're at the same frequencies. You would see them line up at the same points. So yeah, now we've converted the whole thing into a whole different geometry, and we immediately get the S1 transition. That's really cool. This would take long otherwise, right? You don't even have to change the layout to simulate this. Okay, so if you've gotten this far, then you've already done a lot, and you've already seen end-to-end how to use ABCD matrices, and that's really cool. Everything beyond this is some more advanced analyses. Yeah, questions?
What they physically change, like for these strong resonances?
Yeah. So what physically changed is now you have photons that they go across, and you have this hanger structure. It's a very different circuit topology. So the physics will be very different. As we will see in the later cells, what this is actually is just a quarter wave resonator that's hanging off of your feed line, just like we showed in the slides, and just like we showed even data on. Something that's interesting here is this inductor at the end. Who believes that this inductor actually, I don't know how to ask this question. So I'll just say this inductor, it actually is shorted out at the end. You can see that it's connected to also the ground potential. So it's not actually contributing. A fun exercise or something that's done in the cells is we recreate this ABCD matrix without the inductance, and we see that the S1 curves overlap exactly. So what this is actually is just a quarter wave resonator. And a quarter wave resonator that's hanging off a transition line works the following way. It just transmits really perfectly away from its resonance frequencies, but at its resonance frequencies, of which there are higher harmonics, there's this destructive interference, there's just and so we've converted our weird random circuit into a well-defined quarter wave resonator. Yeah. You had a question?
I think that covered
The same one. So now I will continue on. And in the notebook, there's this intermission here. So in the intermission, this is the root cause of all your import problems, because what we do here is now we'll switch to the provided ABCD package that it's just like maybe 300 lines of code long, like it's provided in the same cell. You can read through it, and it uses the same functions that we just implemented. Something that's really cool about this package is it draws the circuits as you multiply the matrices together. That's why you need this SVG write thing. So it's really cool if you have it, and you should probably try to get it to work, but let me just show how it works. So I'll just initialize the ABCD matrices for different circuit components, series capacitance, parallel capacitance, series inductance, parallel inductance, and transmission line with some random, values, just so we see how it draws. And so now I can literally just, and here the multiplication is done much easier. I've overwritten the multiply sign for this class such that you can really just multiply these matrices together like so, right? And so now you can get a total ABCD matrix just by multiplying them together as you want to do it, and you get this circuit topology. And now let me show you that if I comment out one thing, now it's gone. And I want to zoom out here just so that we yeah, so I can just I can remove, for example, the parallel capacitance. So you can see here that it just creates the circuit that as I multiply it. So if I add a series inductance in the middle, pops up right there, right? So and now if I have a parallel inductance here, it pops up there. If I move this parallel inductance up, then it moves where. So this tool really helps you visualize the circuit as you're building it, which is really useful. And then you can take this circuit that you've just created and also translate it into the hanger geometry by using the function ABCD T junction. That's just the function that calls. So you just pass an ABCD matrix to this, and it creates the hanger geometry of that. So let me just, again, make a simpler circuit here. So this is our quarter wave, or this is the capacitance and the transmission line. If I translate that into a hanger, then we got a beautiful quarter wave resonator right here, right? Okay, so then you can, so let me, yeah, make a big circuit here. And then you can also use something called ABCD inverse just to flip it around. So here we're multiplying two of them together, and it automatically creates the joint. So let me just multiply two copies of the same circuit together. I immediately get the circuit. Just for visualization purposes, there's ABCD inverse, which just flips it up so that things are nicely spread out. So now we have a giant circuit, right? And we've built it very easily. Cool. So feel free to draw different circuit topologies over here. We've already played around with it a little bit. So you see this SVG right thing is worth the upfront cost of it, believe it or not. So now let's reconstruct the circuit we had before. And here I'm just showing how we perform the S21 simulation for this specific class. The syntax is just a little bit different. In contrast to before, we initialize the ABCD matrices just with their circuit parameters, not with their frequency arrays. And only when we perform the S21 simulation do we pass a frequency array. This is just a minor syntax thing. It makes things a little bit easier, potentially a little bit faster. Also, what you do is you just call abcd.s parameters and then the frequency array and the port impedances. And what that returns is actually a vector of S parameter. It also returns you the S11, the S12, the S21, and the S22 parameter. Remember, the S21 is the transmission, so that's the voltage out divided by the voltage in. But S11, for instance, is the voltage going left divided by the voltage going in from the right. So you get the reflection coefficient, right? The reflection coefficient looking from the left. And S22 is the reflection coefficient looking from the right. Right, so you get all these, and so we just extract with the right index, we extract S21. So this is just an example, so you see how with this, extended class, you do S21 simulations, but we get the same result as before. Everything works as expected. And now I said that this is actually, the inductance does not contribute to this S21 trace because it's shorted out. Let's test that hypothesis by also creating this quarter wave resonator. And now when we overlay them, you see they align perfectly. So I stand confirmed that the inductance does not contribute here, and it's just a quarter wave resonator. Okay, after this intermission, now it gets really interesting. We'll analyze this quarter wave resonance a little bit. Okay, so let's show it. The first thing we want to do in this exercise is implement the analytic equation for the resonance frequencies. Remember, I showed you that there's this, this is in principle the equation for the higher harmonics of your quarter wave resonator. But I also said that the effective length is increased by this coupling capacitance, right? So you want to insert the effective length here, right? So you want to compute the effective length by adding the contributions from the coupling capacitance, and then you can compute the higher harmonics. So that's how you approach this problem. So let's take a look. Here we are computing, so
one question from Zoom.
yes.
Can you show how one would model the inductive coupling between a quarter wave resonator and a transition line, where the current antinode is at the end near the QDW and the voltage antinode on the other open end?
Yeah, I can. It's a good question. So here's my Slack. So can you please just look away? No, I'm kidding. Where is it?
You don't do it.
Yeah. So I'm assuming you're asking about this. Here you have a derived an ABCD matrix for, this is a new ABCD matrix that I haven't shown yet. So this is if your resonator is coupled inductively to the transmission line. So there's a mutual inductance between your transmission line and then a general hanger circuit. And this general hanger circuit is just described with this ABCD matrix. So you could insert transmission line here, for instance, and then a capacitance at the end, which would realize the quarter wave resonator, but it's not capacitively, but inductively coupled to your feed line. And then this is the ABCD matrix for that. You can follow the derivation. There's a derivation to do this, but you can see there's a whole family of ABCD matrices for all kinds of circuits. And yeah, this one extends it. I hope that answers the question. So back to calculating the quarter wave resonance frequencies. First, we calculate the effective length by taking the length of the quarter wave resonator and adding the capacitive correction to it. Let me just zoom in a little bit more. Maybe that'll help. Adding the capacitive correction, and then we just calculate the frequencies using this new effective length. So you really want to think of like the capacitance as effectively extending the length, right? So we run this, we check it, and it's correct. I always like to see if changing this, if my tests actually work. And they do. So now the task is to calculate the first 4 resonance of the above quarter wave resonator. That's the task right now. And we have a functioning function. And so what we want to do is we want to calculate it with and without the capacitive correction. So here there's a list, the frequencies with the capacitive correction and without the capacitive correction. And so for the first 4 mode indices, we just call our function and selectively add the capacitance in or not, right? And we provide it in gigahertz, which is the task. We need to provide it in gigahertz. And then we append this to our list. So we're just calling our function for the first 4 modes with and without the capacitive correction. And it's correct. And you also get for you printed a table of what you just calculated. And it involves, yeah, and it shows how much this capacitive correction actually shifts your resonance. And you can see it's quite a lot. It's a few hundred megahertz here for a 30 femtofarad capacitive coupler, right? So that's quite a lot. Admittedly, a 30 femtofarad coupler is quite large, but it appears a lot in superconducting devices. I have capacitive couplers that can go even well beyond that. Like the Purcell filters generally have large capacitive couplers up to 50, 60 femtofarad. So yeah, you really want to capture this capacitance effect. We're not including capacitance to ground here, mind you, so that would even come on top, right? We're just looking at the coupling capacitance. So now we just plot, there's nothing you need to do here. It's already all filled out, so we plot it, and we see something very interesting. So what you see is plotted on top of the transmission from earlier, that the capacitive correction really matters, right? And it's really good too. It's a very simple formula. It's just the length plus a simple capacitive correction and then the higher modes, but it accurately predicts these higher harmonics that we can confirm with simulation. So that's a fun little demo, but we're not barely halfway through our notebook, so bear with me. What we'll do next is we'll construct LC oscillators and half-wave resonators, LC resonators and half-wave resonators that have the same fundamental frequency as our quarter wave resonator. Why do we want to do this? Like I said, in practice, what we care most about is the one fundamental mode. That's the one we use. The higher harmonics are more an artifact that arise because we use distributed elements. So in this section, we need to convert, we need to find the circuit parameters to align the resonance frequencies, right? And so there's a quick intersection that I want to make here, which is Posar actually provides a little help on that. So here, there's a formula from that book. And this formula, it says here, we can identify the resistance. So you can ignore resistance. We don't have resistance because we have superconducting circuits. There's no loss. But we can identify the circuit parameters for the equivalent LC circuit that approximates the fundamental mode. So for a quarter wave resonator. So the effective capacitance here of a quarter wave resonator at its fundamental mode is calculated using this formula here. So you just insert the frequency of that fundamental mode and the characteristic impedance of your transmission line, and then you get this capacitance. So the capacitance that approximates the mode capacitance at fundamental resonance. And similarly, there's an equation for the inductance, and it's just derived from the resonance condition for an LC circuit. You can confirm this. It's just derived from this thing here. So really cool. We can identify the effective capacitance and inductance of any of these resonances and then approximate them using an LC circuit. That can be useful, for instance, if we prefer to do circuit quantization with lumped elements instead of distributed elements. You might want to take your, distributed resonator and transform it into an LC circuit, knowing that this is an approximation, right? And this might not be perfect. So, so that's what we do here is we just apply those formulas given right here for the frequency, the fundamental mode frequency, and we use the same coupling capacitance. Note that we use the unloaded frequency. Why? Well, because we're using the same coupling capacitance. So we expect this LC oscillator to also experience the same shift due to that coupling capacitance, right? So now we compute the mode capacitance and the mode inductance using those formulas, and right, and now we create that circuit. So I want to comment on this circuit for just a second. So I'm just showing you how we're building it. It's you have a T-junction, so you transform all of this into a hanging circuit. So what's the circuit? It's a series capacitance, and then a parallel inductance, and then a series capacitance. Now, you might say, hold on, this doesn't exactly look like my LC circuit, because this one looks nicer, right? Well, you're right, it doesn't, but it behaves the same. So this thing, important is that they're coupled to the same potential at the bottom. So we can just hack it with this thing. There's also an ABC matrix for two parallel things that don't terminate, for two parallel things that look like this, that they have the same, they're just two branches that start at the same potential and end at the same potential. There's also ABC transformations that do that. So there's an ABC matrix for anything you want to do. But this also serves our purposes, and using the calculated in mode inductance and capacitance, first of all, we check that it's correct, and then we simulate the S21 trace, and beautifully, we see that it aligns very well. And importantly, this includes the capacitive correction. So we can see that we very well approximated the fundamental resonance of our circuit using these equations from Posar. Now we can do the same thing for a half-wave resonator. I mean, I can pause for a second if people have questions, but it seems like everything is going all right. So for the half-wave resonator, the only thing we're basically doing is we're doubling the length of this transmission line. So instead of 4 millimeters, we're now using 8 millimeters. And for the capacitive corrections to work out, we're using the same capacitance at the bottom and the top. You can play around with this and see, how exactly the capacitive corrections play. And I haven't talked extensively about how the capacitive corrections work for a half-wave resonator, but it's basically the same thing. It's you just add VP, so phase velocity times the characteristic impedance times the capacitance at either end. They both add effective length. That's it, right? And you'll notice that you need to use the same capacitance at either end, so that by just doubling the length, the fundamental resonance is aligned. You could also use less capacitance and then just compensate with a longer resonator. You could play around with that and see that that works. So we test this and we see that they align beautifully. Even the higher harmonics align well. But we could also build a half-wave resonator if we prefer to do so, to use, for instance, as a readout resonator at the frequency 7.5 gigahertz, or it's like around 7.1 with the corrections. Cool. So that's up to that point. That's
what roles that the are in resistant in the transformer, right?
Yeah. So the R is, for instance, if your transmission lines are lossy, they have loss. This alpha here is like a loss number. And so at room temperature, your lines have some finite resistance, right? So if you send current through them, then the current will experience that resistance, and will taper off. It will get lost the farther you send your signal through that line. With superconducting circuits, and I feel like this is something we often just take for granted, that resistance is actually exactly 0, and that's that one Nobel Prize. Like, that fact is pretty impressive. It's also really crucial for any of this to work, right? Because we are working with such weak currents, such weak voltages, that they represent individual photons, maybe 3 or 4 photons that we use to read out a qubit, right? If we had any resistance at all, those would get hopelessly, overwhelmed by the resistance, which is also why, we need superconductors to do any of it.
So in this case, you are in if your line is
R is
with a series of parallel.
right. So let me show it. So this is Posar. It's dauntingly long, and there's a lot in here. So that formula was for this circuit. It's a parallel RLC circuit. So you want to set R to infinity, such that this is an open, and it's just, you can ignore it from the circuit. Why can you see that this is infinity? If you set alpha to 0, R becomes infinity. I told you alpha quantifies the loss, right? So alpha enters, I believe, an exponential. Not sure. Yeah, I think alpha enters an exponential. So that's the exponential loss you experience by sending down a signal through a lossy, a resistive line. But we have no loss, so we just set alpha to 0. R becomes infinity. Okay, so let's try to move on. So now what we're going to do is we're going to fit the resonance, the Lorentzian line shape that I introduced. This is this part here. Now we don't want to just predict the resonance frequency. We actually want to fit to our circuit. And so we generate the trace using ABC matrices, but then we fit this shape to it. Or more exactly, we fit this shape to it so that we can account for the asymmetries that arise in, if your feed line has some impedance mismatches, if there are these interference patterns on the feed line. So the first task here is to just implement that S21 Lorentzian, and it's as easy as just writing down that formula that I just showed you. Right? So we just write that down for an array of frequencies. Again, kappa is the line width that sets how broad your resonance is, and phi is the asymmetry. And we'll see that now. So first of all, we check that it's correct. And then we will just evaluate this function. We'll plot it at different values of kappa and phi just to see what the effect is, right? So here, the to-do is, you have different values of phi and kappa, and you're just supposed to evaluate your function at different values of these. And so that's what we do here. We set phi to 0, and then we evaluate the Lorentzian at different values of kappa. And then later on, we set kappa to some value that's given, and we evaluate it at different values of phi. So we go ahead and do that and check that it's correct. And then we plot it. And here you can see how, different values of kappa just broaden this Lorentzian. And you also see, I've here just shifted the S1 functions so that it's easy to understand what's going on. But you can also see that phi sets this asymmetry, right? So now we'll use this function to fit to the quarter wave resonance and actually see, how broad, what's the line width of this resonance. We've seen what the resonance frequency is. We want to see what the line width is. So let me just replot it again. We'll zoom into the fundamental mode. And again, this is the trace that was now. This trace was generated with our ABCD matrices. This was not generated using the Lorentzian we just performed, but it looks like our Lorentzian will fit nicely to this. So here I'm just showing you, there's nothing to do here, how we fit, like, we're not actually going to use the function we just implemented. We're going to use the back end. There's a back end function that is just called fit resonance. And you just pass in the frequency array and the transmission values. And then it provides to you a dictionary with all the fit parameters, including kappa, line width, and the resonance frequency. And it also provides to you the fit trace that you can use for plotting. So you just call fit resonance and then pass in your two things. And then from that dictionary here, let me zoom in a little. From that dictionary, we extract the resonance frequency. And we also extract the kappa. And we translate them to units of gigahertz and megahertz. And then we plot them. Or we print them. And we see here that we get a kappa of roughly 20 megahertz. This is a common line width you might want to choose for a Purcell filter. Okay, and now we can plot the trace on top of our simulation, and you can see that it fits really well. Okay, so now what we'll do, that's a little more interesting, is we'll perform that simulation that I just showed you, where now we have a semi-infinite waveguide, so we have this capacitive interruption, and now we will sweep the quarter wave resonator. We will sweep its coupling position from left to right. And for each coupling point, we will fit using that function we just used and extract the kappa, and then we'll plot this. So we'll reconstruct this plot. So here's the rough circuit topology. The only two variables that we want to change are LF1 and LF2 that set the coupling position on our feed line. And everything else we keep fixed. So yeah, here as a first step, we'll just do this fit for one coupling position and visualize it. And then we'll sweep. And so here the exercise gives you LF1 and LF2 as distances. So we can just go ahead and construct this whole waveguide, or this whole circuit. So you can see here what we're doing is we have a series capacitance. This is our input capacitor. Then we have the transmission line. This is the first section of the feed line. Then we have a hanger circuit, right? So we have this shunted network, and it consists of a series capacitance and a transmission line, right? This is the hanger circuit that we've defined. And then there's an output section on the feed line. And that already defines this whole structure. Okay, so we've defined a function which will make our lives a little easier. We just need to pass in the circuit parameters. Okay, and that already ran through. I have a few more cells here. So the way I like to use these ABC matrices generally is I define a function that performs this network multiplication. And then I just define a dictionary of the parameters that I then pass in to this function to instantiate it. This is how I like to use it. So there's a frequency array that's provided here. And then we just instantiate this whole ABCD network, and we get its S21 trace, like so. This, we're getting the S21 parameter. And then here we use fit resonance. So we pass the frequency array and the simulated S21 data, and then we fit it. And like before, we extract the resonance frequency and the line width. Then we print it, and we also plot the trace. So what do we get? Interestingly, we get a slightly reduced line width, right? This is no longer 20 megahertz, now it's 18, right? That's less. And also, we see that we beautifully can account for the asymmetry. We can fit to it well. This works nicely. Note, I want to take a moment here and note that now the simulation has gotten even larger effectively. We have a quarter wave resonator. This is already a large element if you would print it on a chip. But we've now added a 12 millimeter long feed line to this. So if you would do this in a layout, that would just blow up entirely. So doing this simulation effectively, just as fast with ABC matrices is really cool. And I keep highlighting this over and over. So that's correct. That's great. And now we will perform the sweep. So for the sweep, we want to make sure that the total length of the feed line remains the same, but we're just changing the relative weights of LF1 and LF2. Right? So we're just keeping this sum constant here. So we instantiate an array from 0 to 12 millimeters. That's the total length, right? We create a list for our kappa values. And then for each LF1, so for each coupling position, we instantiate again our parameters using the same fixed parameters as before. Now LF1 is this variable, and we keep the total length constant by just calculating LF2 in this way. We just subtract the total length, and then from it we subtract what LF1 was. And then we also pass the characteristic impedance and the phase velocity. And we use these parameters to instantiate the circuit. So for each coupling position, we now have an ABCD matrix. We have a frequency array, the same one as before. When we extract the S21 parameter from that. And then we fit the resonance again, like we did before. We're just doing this per coupling position. We extract the kappa value and then append it. That's all we're doing. So this takes a little longer. You can see for 100 coupling points, this took 1.9 seconds. Try doing 100 finite element simulations of something that's 12 millimeters long, and then we can compare run times. So it's correct, our kappa array, and now we can plot it. And you get this beautiful, this is not an analytic function. This is actually what our fits returned. You get this beautiful cosine. That's really large, but you get the idea. Beautiful cosine. So now there's a question, and I just want to check the time. So Nick, what's roughly the, I mean, we're close to 12. I'm very close to wrapping up. Can I take like 3 more minutes or? Okay, so the question here, yeah, maybe I'll just leave this as an open-ended question, but we can reason about what's interesting is the length of the quarter wave resonator is 4 millimeters. And what we see here is the point of destructive interference is 4 millimeters. Anyone have an idea why that is the case? So think again, why this destructive interference happens. What's happening is you have photons that leave the resonator and they go to the right, but at this point they have no phase. And then you have photons that go to the left, travel and come back, and then they meet the rightward traveling group with a relative phase. So why is it that when this length here corresponds exactly to the length of the quarter wave resonator, so to lambda over 4, why is it that there they perfectly destructively interfere? So, yeah.
Because one is open and one is terminated to ground. We kind of look at the point. We go one way, there's it's terminated by a capacitor, and then one is a quarter wave and one is the half wavelength resonator. Kind of look at
Where's the half wave?
like if you go along the blue, one.
Okay,
if you
yeah.
go along the black,
Mhm.
another one.
Mhm.
Then
Yeah.
go.
So this here is not really a resonator, right? I mean, what you really want to think about is what is the relative phase that these photons are accruing as they travel.
Maybe
So-
because there's a 180-degree phase flip, a reflection, and then because it's 2L, so it'll completely overlap. Like if we're in
Yeah.
the same direction, there would have been no phase change.
Yes.
But because there's a reflection, so there's 180 degrees.
So the capacitance here doesn't really add a phase kick. If this was a shorted boundary, it would add a phase kick. So there's no phase kick, but it accrues phase as it travels here. So remember, this is lambda over 4. And if this length also happens to be lambda over 4 long, apparently the phases are such that they destructively interfere. Why is that? You had an idea?
Is it because that the reflection travels 2 and then the transmission is 1, so like they exactly overcome the pi phase?
Yes, perfect. So if you travel 2 times a quarter wavelength, you've traveled a half wavelength. And if you've traveled a half wavelength, you've acquired a phase of pi. And so that translates into some factor of -1. And since they've been reflected perfectly, now you have a group that has, you have 2 groups that have a relative phase shift of -1, and they have the same magnitude, so they perfectly destructively interfere. So this is what you want to think about, is like, what are the relative phases? And you can also study the other points here at 8 millimeters, you have, perfect constructive interference and so on. So you can reason about this, which is nice.
So isn't the phase difference between quarter and a half wavelength pi by 2 rather than pi?
Yes, but you have you start with the situation where there's 2 photon groups on your feed line at this point. They've already left your
Oh, I
resonator.
see.
And now you
Zero
just want to know
versus-
what's the relative phase they then acquire by doing this round trip. And it's a half wavelength of relative
I
phase
see,
that they
okay.
acquire.
Makes sense.
Okay, so that would come into here. And then there's an optional question. We'll skip that. And I'll just show you the last exercise I think is really cool. And if you find the time, I encourage you to do it. Is we'll use the ABC networks we've developed and the tools to actually implement a trace from a paper. And this is not any paper. This is the first paper that introduced Purcell filters. They were different. They were not like the ones that I showed you. But here's a network that they show. And the exercise consists of reconstructing this network and then simulating this transmission here. And the filter works by adding a suppress. So this is the filter here. There's 2 copies of them just to improve the filtering. And what they do is if this lambda is chosen according to the frequency of the qubit, in this case, these filters introduce like a notch, like a dip and attenuation at the frequency of the qubit. So the qubit which sits here can't leave through this side because these filters are suppressing that. And this was the first experiment that actually performed Purcell filtering, which means just suppress the qubit frequency. And it's very simple to reconstruct. We just ignore the qubit here, and then they give all the lengths and capacitances in the text. So you would just reconstruct this circuit, and let me show you the results. So there's some tips on how to read through the paper, it's just 4 pages long. So we can first build the cavity. This is the resonance. It looks differently because we're looking through it. And then that's a cavity. And then here's this notch filter, which looks like this. And we can just piece them together. This implements exactly the circuit from that paper. And we recover the same trace as from the paper. And if you successfully run this, then let me just run these cells. There's a little Easter egg at the end. So those who don't want to get spoiled, just cover your eyes and ears. And those who do, don't. So yeah, and yeah, I don't know if any one of you reached this point, but you were awesome and SQDev loves you. So yeah, that's all from my side. You now have a complete notebook. Hopefully, you can get it to work. It's really called this SVG write thing. But yeah, that's all I got.
So what happens if we have like multiple qubits and multiple drive lines? Does it help in that case as well?
Yeah, well, so I also had examples in my slides of how we designed, for example, qubit couplers, and we dealt with crosstalk, and we can simulate circuit crosstalk. So you can use this also for not just resonators, but also measuring crosstalk, for instance, and all that.
Oh,
and again, just as like a recap, you can do all of this by laying out the device and then simulating it. But if you know how to translate it to circuits, then it goes much faster and it's still accurate. All right, I can wrap up.
Okay, that's it. So thank you, Peter. Yeah.